After centuries of brilliant attempts, a general method for computing areas of curved shapes was achieved in the 17th century. That method is called integration.
It's often been said that Isaac Newton was born in the same year that Galileo died, as if it were necessary to have one person of that caliber on Earth at all times. The Newton family was a farming family in Lincolnshire, neither particularly poor nor particularly prosperous. Isaac himself was a strange lad, and his mother, who had the job of bringing him up, soon realized that he was too lazy ever to make a decent farmer, and so she did the only thing she could with him. She sent him to the university. If Isaac's father had lived, he might very well have grown up to be a well-adjusted and extremely clever farmer. Instead, he went on to do things that stagger the imagination. One of them has to do with inventing the calculus.
In the latter half of the 17th century, an eccentric English scientist discovered the calculus. His name was Isaac Newton. And his discovery is without parallel in science and mathematics. But credit for discovering the calculus can't be granted to Newton alone. It's rightfully shared by a scholarly diplomat from Hanover, an electorate in the German state of Lower Saxony in the 17th century. His name, Baron Gottfried Wilhelm von Leibniz. Worldly, outgoing, quite a fellow with the ladies. Leibniz was different from Newton in almost every realm, except that of genius. Like Newton, Leibniz was a mathematical prodigy. But unlike Newton, whose forte was theory, Leibniz frequently displayed a practical nature. For example, Leibniz invented a mechanical calculator. His calculator was portable and could actually extract square roots. He was acclaimed throughout the courts of Europe for inventing it and was invited to join the British Royal Society. No small feat for a German. However, it's for the calculus, not the calculator, that Wilhelm Leibniz is best remembered. Although Leibniz and Newton are recalled as its chief architects, neither one built the calculus single-handedly. Because, like all other magnificent mathematical structures, the calculus is a culmination of ideas. Orain, Galileo, Kepler, Descartes, Fermat, and many others before Newton and Leibniz had asked questions about speed, acceleration, and the behavior of changing quantities. Questions concerning rate of change, many of which are now answered routinely with differential calculus, can be reduced to a geometric problem, which is to find the tangent line at an arbitrary point of a curve. However, not all geometric questions involve motion. Some involve things that are fixed in place, like the land itself. In ancient civilizations, such as Egypt, geometry had a number of very practical applications, including how to measure the land. The very word geometry, in fact, is the Greek word for land measurement. In the Golden Age, when Greek traders asked questions about specific areas and volumes, Greek mathematicians were able to offer specific answers.
The area of a rectangle is the product of its base and its altitude. A triangle has an area half that of a rectangle with the same base and altitude. Any plane figure, bounded by polygonal lines, can be divided into triangular pieces, which makes its area the sum of the areas of all the pieces.
But how does one find the area of a curved figure, a parabolic segment, or an even more exotic shape? These mathematical questions were challenges to the mind and spirit of Greece. In an intellectual marathon, which may be thought of as a relay race toward the calculus, Greek mathematicians competed to find a general method of quadratures, a process for calculating areas of curved figures. There were strong entries from other cultures, but the first lap was a victory for the Greeks. Their idea was to approximate the curved figure with inscribed polygons, attempting to exhaust the whole figure. Bit by bit, they used an increasing number of sides. This ancient Greek approach is called the method of exhaustion. With the method of exhaustion, an application of the concept of the limit of an infinite sequence, the Greeks set the mathematical standard for centuries. And they almost reached the calculus. In fact, if Archimedes had known the symbols that would be in common use 18 centuries later, he probably would have succeeded. In any case, even without the help of algebra, he made a number of spectacular discoveries. One of the more remarkable was the quadrature of a parabolic segment.
Let A of t denote the area between the parabola and the x-axis, from x equals 0 to x equals t.
Archimedes showed, by an ingenious geometric argument, that this area is equal to 1/3 t cubed. But as valuable as the parabolic segment was in the advance toward the calculus, it's a special case rather than a general shape. So, an even more powerful mathematics was needed to thrust scholars forward. It would come along, but it would take a very long time to appear. Not until the early 1600s did a wandering mathematician and astronomer, Johannes Kepler, get the ball rolling once again. Johannes Kepler computed the areas and volumes of 92 new curved shapes. Kepler came close to the calculus, but like the Greeks, he couldn't invent a general method for all shapes and functions. But this time, the race wasn't delayed, and two Frenchmen picked up the torch, Pierre de Fermat and René Descartes, blended algebra with geometry, which finally made it possible to describe geometric figures with algebraic equations.
In a rectangular coordinate system, a line of slope m can be described by the simple algebraic equation y equals m times x. And an algebraic equation for a circle comes directly from the Pythagorean theorem for right triangles.
Fermat came closest to reaching the derivative with his general method for locating the high and low points of functions, points where the slope is 0. The race for the calculus was entering its final lap. The scientific progress sped across the Channel, where it generated excitement at Trinity College. The great mathematical advances, most notably the work of Kepler and Fermat, happened to arrive in Cambridge on the heels of an obscure lad from the farm country of Lincolnshire. He was Isaac Newton. And among other accomplishments, any one of them enough to earn him a chapter in scientific history. He would go on to discover the universal law of gravity and to reach the calculus. Later, to a much older Newton's dismay, if not utter contempt, so would Wilhelm Leibniz. Although Newton claimed, "If I have seen further than other men, it is because I stood on the shoulders of giants." It wasn't this man he had in mind. Copernicus, Galileo, Kepler. In Newton's mind, these were the shoulders upon which he'd stood. Leibniz and Newton, victors in the race for the calculus. While their discovery was made in the same field, it was hardly made in the context, much less the spirit, of good sportsmanship.
Yes, indeed, sir. I have spoken to him. I'll go and see him again.
It was a drama with a conflict that could have been written by Shakespeare. And this was a drama of no small academic consequence. For as the reputation of one player was in peril,
My dear Englander, you are a guest in my house.
so too was the very sanity of the other. Earlier, however, before the situation went beyond reason, Newton's mind was capable of the most rational thought imaginable. As a young man, influenced by Isaac Barrow, the Cambridge mathematician whom Newton hardly acknowledged as his mentor, Newton discovered his very own calculus. He called it the method of fluxions. Newton saw that the rate of change of a function gives the slope of its graph, and realized that the slope itself generates a new quantity, the fluxion. Today, Newton's fluxion is called a derivative. This mathematics was stronger than the Greeks, as quick as Kepler's mind, and more flexible than Fermat's work. With this mathematics, Newton explained the motion of objects in space and won the relay race that had begun 2 millennia before. This mathematics was the calculus. And yet, Newton kept his calculus to himself for 30 years. The question is, why? No one will ever know for certain. But Isaac Newton, rational scientist, left letters, hints, confessions. In his own secret words, he revealed fantasies of burning his mother. He jotted 2 million words on alchemy and biblical prophecy, and denied certain teachings of his church. And that wasn't all he denied himself. On his deathbed, at the age of 85, Newton claimed his greatest triumph was to die a virgin. Isaac Newton was, nonetheless, one of the more productive men in history, despite an obsession with secrecy, terror of scientific criticism, and of thievery. For 30 years, in letters to his friends, he dropped cryptic hints about his discovery of the calculus. Perhaps too many hints. Of course, as a diplomat, Leibniz dealt with secrets, but in a different way. He also dealt with Newton, though never in person. They corresponded for years, but never met. Newton wrote Leibniz a challenge, an anagram, hinting at fluence and fluxions. But this time, Newton might have been too clever. Intrigued, Leibniz mastered the previous work of Kepler and Fermat, and invented his own calculus. It might not have been the first, but one fact rises above debate. It was the first to be published. Leibniz's was slightly different from Newton's, and in some ways slightly better.
Leibniz incorporated the idea of calculating area by imagining a picket fence of little rectangles. Imagine them diminishing in size and add their areas. Eventually, their sum approaches a limit, which is equal to the area of the region under the graph of a function. This is the process of integration. Leibniz summarized it with the integral sign, an elongated S from the Latin word for sum.
Both Leibniz and Newton, each a genius with a new idea, recognized something the others had overlooked. They saw the surprising connection between integration and differentiation. This remarkable connection can be understood by calculating the area of a parabolic segment.
Let A of t denote the area between the parabola and the x-axis, from x equals 0 to x equals t. This is a function of t. Try to find its derivative, dA dt. If the area from 0 to t is A of t, then the area from 0 to t plus delta t is A of t plus delta t. The area delta A is the same as the area of a rectangle of base delta t and height x squared for some x. As delta t shrinks to 0, x squared becomes t squared. In other words, the derivative of the area function is t squared. Trying various functions to see which one has t squared as its derivative, 1/3 t cubed eventually comes to mind. That works. And so does 1/3 t cubed plus a constant, because the derivative of a constant is 0. The area function A of t is 1/3 t cubed plus a constant. Since the area is 0 when t is 0, the constant is also 0.
So there it is, the quadrature of the parabola, using the calculus of Newton and Leibniz. In the language of calculus, the integral of x squared from 0 to t is 1/3 t cubed. Of course, Archimedes had already done this by a geometric method, but the calculus is superior. Calculus applies not only to the parabola, but to any smooth curve. It solves the problem of quadrature in general. And it reveals the long-hidden connection between integration and differentiation. Differentiation and integration are inverse processes.
Start with a function and integrate to get its area function. Then take the derivative of the area function. The result is the original function. This phenomenon is called the first fundamental theorem of calculus. On the other hand, the parabola illustrates something else. First, the area of the parabolic segment was calculated from x equals 0 to x equals t. To find the area between any two values of x, say from x equals 1 to x equals 2, simply subtract. Take the area from 0 to 2 minus the area from 0 to 1. When this idea is expressed in its general form, it's called the second fundamental theorem of calculus. It says that a function is equal to the integral of its derivative plus a constant.
Newton and Leibniz realized that the second fundamental theorem, which was discovered by solving the geometric problem of quadrature, also has important consequences in the mechanics of moving bodies. Since the derivative of velocity is acceleration, velocity can be obtained by integrating the acceleration. And since the derivative of displacement is velocity, displacement can be obtained by integrating the velocity. Newton was aware of the profound power of this new mathematics. But as he sat polishing his calculus, as if it were a most precious apple, all the while posting cryptic hints of its golden flavor, Leibniz published his differentials and integrals. 3 years later, Newton somewhat reluctantly published his mathematical principles of natural philosophy, the Principia. And yet, except for a few hints, Newton kept his calculus to himself. While Newton remained secretive about his work, the same could not be said of his countrymen, who praised him at the expense of Leibniz. They created chaos in the Royal Society over the matter of who first invented the calculus. The Newton-Leibniz controversy was bitter in taste and mean in spirit. One of its low points was the charge that Leibniz had plagiarized ideas from Newton's letters. Leibniz was outraged and demanded a formal hearing. Of course, since Isaac Newton himself was president of the Royal Society, Leibniz might have made a wiser move.
This has come for you by hand, sir.
Oh, thank you.
Even before pleading his case, Leibniz was judged guilty.
The messenger would know if you wish to send a reply.
No reply.
Thank you, sir.
And so, Leibniz, who'd begun his career in mathematics with the philosophy of optimism, ended it with an equation of bitterness. Hearing of the German's death, Newton boasted, "I had broken Leibniz's heart." Ironically, though Newton's fluence inflections were to rule Britannia for a century thereafter, Leibniz's notation was better, and it became the universal language of mathematics. His symbol for the integral conveys a sophisticated idea. The integral is the area of the region under a curve, and at the same time, it's an antiderivative. And so, the race for the calculus that began in ancient Greece finally ended in a controversial photo finish. There could have been more than enough glory for both winners. But while the glory wasn't shared, the prize was. Not between Newton and Leibniz, but among every generation since. The insight of Leibniz and Newton, most notably the connection between differentiation and integration, has evolved into a tool of incomparable value in mathematics. Thanks to both Leibniz and Newton, differential and integral calculus are the collective language of science.
Newton's calculus was first published in this book, which, as you can see, is called The Method of Fluxions. It's about Isaac Newton's theory, but it's not written by Isaac Newton. It's written by this man, John Coulson. For reasons that are not entirely clear, Newton's own manuscript about his calculus was never published during his own lifetime. It may be that he just got the manuscript ready, handed it over to the publisher, and then the publisher was a little slow in getting it out. That sometimes happens. In any case, it did finally come out. It came out in 1969. Newton's fight with Leibniz over priority for the calculus was by no means the only fight that he had during his lifetime. There were many of them. Newton was a great genius, but he was not a very nice man. One of his most famous quotations was, "If I see so far, it's because I stand on the shoulders of giants." He may have stood on the shoulders of giants, but he trampled on quite a few other people as well.